Hi, thanks for being with us today. This is a very special CIS colloquium. It's the first one after COVID where we meet in person with an external speaker. It's great to have so many people in the room. Thanks to all of you online as well. As you know, with this seminar series, we provide a platform that brings together professors and researchers working on different aspects of intelligent systems. Today, we are delighted to have Professor Philippe Rigollet with us. He's a professor for mathematics at MIT. The talk of Philip will last for approximately 1 hour, roughly 45, 50 minutes of talk, and we have 10 minutes for question and answers. If you're online, just put your questions in the chat. We'll try to take them up either online if they're urgent, because Philip agreed also to take urgent questions from the audience, and otherwise we take them at the very end. Don't forget, those being here, don't rush away. There's a small apéro if you want to stay and want to have a glass of water or anything else before leaving and have a further chat with our speaker. And now, before we dive into the presentation, thanks a lot, Philippe, for being here today. And I pass the screen to Nicolas for some words of welcome.
Hi, everyone. So I'm very pleased to welcome Philippe. So Philippe is a full professor of mathematics at MIT. Previously, he was an assistant professor at Princeton. He did postdoc at Georgia Tech and his PhD in Paris with Tsibakov. And he's currently in sabbatical visiting INRIA and the Fondation Sciences Mathématiques Paris. Philippe won many awards. He got Best Paper at Colt, NSF Career Award. What? Oh, sorry. NSF Career Award, Best Paper at Colt, and he is also he gave or he will give the Medallion Lecture at IMS. So we are very pleased to have Philippe with us today. Please, Philippe.
Thank you. And so thank you, everyone. It's also one of, so I gave only one other talk since COVID, and it was a much smaller crowd. So I'm very happy to see a lot of people. It's always very energizing. I like my talks to be interactive. So if you have any questions, urgent or not, please feel free to interrupt. So I'm going to try to give a fairly broad talk. So it might be, so if you already know optimal transport, or if you're familiar with some of the things that I've been working on, it might be a little pedestrian for you. I'm trying to give in this talk an overview of the kind of new questions that optimal transport have brought within reach within statistics. So I'm a statistician and also machine learning. So the way I'm going to structure my talk is by giving an overview of what optimal transport is, and then moving on to several applications. Since I mostly prove theorems for a living, all those applications are certainly not driven by me, but by my collaborators or even people I don't work with. And finally, I'll try to touch upon some interesting questions moving forward, maybe even beyond optimal transport, certainly not beyond statistics or machine learning. All right, so story starts in the 18th century with this probably famous paper of Gaspard Monge, Mémoire sur la théorie des déblais et des remblais. And so he introduced this new problem, and we'll switch to the modern version of it immediately. So we have mu, which is a déblai, so it's a pile of dirt, and we want to move it to a remblai, which is a ditch. And so those are probability measures. We're going to assume that they have the same volume, so all two probability measures of measure one. And the goal is to build a transport map, so something for each location x of a grain of sand on the first on the déblai will move you to a position y through this map t. And what you want is, of course, to actually satisfy your initial and final constraints. So you want this map to actually really do the job, and this is called a push forward map. So we say that t pushes mu to nu, and that's the standard notation for this with this little sharp notation. Okay, so a t is just saying that if x follows distribution mu, then t of x follows distribution nu. That's this notation. So there's many ways to do this, right? For example, you could think of flipping things around. Everything that's in uniformly on a disk could be rotated around and still maintain the same distribution. So there's some ways that are more economical than others, and that's where the optimal of optimal transport comes from. And so what you're doing is you're saying, okay, let's look at the average displacement cost, right? So moving from x to t of x, this costs me norm of t of x, let's say squared, because squares are always nicer, we can expand them. And then I'm going to look at what happens in average over my starting point. So that's my average travel distance. And then I'm going to try to minimize this travel cost among all possible valid transport maps, the one that actually push mu to nu. Okay, very simple problem. And we'll see in a second that it's not so well posed. There's an immediate hurdle, which is if I start with a rock, I certainly cannot transport it there, right? I would need to somehow bring it, and for the same reason that the C-shaped curve is not a function, because for each x there's multiple choices of y. Here you cannot have this, but we have a solution in probability. You can replace this by a Markov kernel, which will tell you where to move each point x to multiple point y's, each with their own probability of moving there. And so we're going to move to the notion of what's called a transport plan. So it's just really a relaxation of taking a function and mapping it to probability distributions over possible outputs. And the simple way to write this is to say, okay, now I'm not going to force y to be a distribution t of x. I'm just going to say I want y to be distributed according to the target measure, x to the source measure. I want to minimize the expected distance between x between all these guys. So if you look at this formula, it's not clear what I'm minimizing over. I'm actually minimizing over all joint distributions between x and y, all couplings of mu and nu. Okay. And this was introduced by Leonid Kantorovich in the 40s. He went on to get a Nobel Prize for this. He was certainly not aware of Monge's work, but turns out it's an immediate relaxation of the Monge problem, and it's much more tractable. This is in fact an infinite dimensional linear program. So from there, you can actually play around a little bit with this cost and get something which is called Wasserstein distances. And Wasserstein distance is simply this infimum. So here I really made the dependence on the coupling, the joint distribution of x and y. It will be denoted gamma, and coupling will play a big role in this talk. So please pay attention to this slide. So here I'm minimizing overall couplings, the expected square distance, travel distance, this time to the power p, and then I rescale to the power 1 over p to have something that's homogeneous and has a chance of being a distance, and it is indeed a distance, okay? And I'm minimizing over this set of couplings. This gamma of mu nu is simply the set of joint distributions whose first marginal is mu and whose second marginal is nu. So this is a bit of a heavy notation, but it's just saying it's the distribution of all pairs xy such that x is distributed according to mu and y is distributed according to nu, and they could be d-dimensional, but those are identified marginal. Okay, so this is the coupling. Here are some examples of couplings that might or might not be optimal. On the one extreme, you have the independent coupling, where I give you two marginals. Well, you could say the joint distribution is just to take them independently of each other. And then if you look at, so that's just the product measure, denoted by this product measure notation. And on the other end of the spectrum, where you don't have to add any randomness, is the deterministic coupling, where y is in fact a function of x. So if you give me x, I know everything. Basically, maybe you could think of it in terms of mutual information if you're an information theorist, right? So there's either none or a lot, and that's what the Monge problem is trying to solve. Okay, and so somewhere in between the spectrum will be our optimal coupling. It turns out that there's this famous theorem in optimal transport called Bernier's theorem that tells you that under some simple assumptions that basically remove the assumption of having this rock that you have to break. So if you assume that mu has a density, for example, with respect to the Lebesgue measure, and p is at least 1, then the solution of the Monge problem is in fact the same as the solution of the Kantorovich problem. And in fact, there will be more. We'll come back to this. It's telling you that the solution, the optimal coupling, is a deterministic coupling. There is a map that solves the original problem. You just need to rule out this possibility of having a rock that you need to break. Okay, the density prevents you from having. Okay, so that's basically all you need to know in optimal transport to understand what I'm going to talk about. And I'm going to actually focus quite a bit on couplings, but I wanted to give you just a little bit before we get there, a bit of an overview of how OT has been used. I'd say mostly over the past 10 years in statistics and machine learning, and how they've pushed our understanding of a variety of problems in very different ways. So I like to talk about statistical optimal transport. There's this book by Perret and Couturi called Computational Optimal Transport, and I'm just going to try to give you an overview of what makes modern optimal transport. So the not too modern optimal transport is contained in these books. Okay, so Villani wrote 2 influential books, and if you are interested in optimal transport, chances are those are the books you pull out of the library, and they're mostly studied from the perspective of mathematics, and in particular analysis, some probability. But at some point, I remember being interested in optimal transport at some point, and I think he mentions mathematical statistics in the introduction. And there's really nothing there. It just refers to, I think, the Pro-Hoff metric or something like this that metrizes the convergence. So so there's very little about statistics going on there. So let me tell you what you could do with optimal transport beyond in statistics beyond well, just this one reference in this book. So the first thing you might want to be tempted to do, if you give a distance between probability measures to a statistician, chances are he's going to build a test out of it. Okay, so a test for goodness of fit or homogeneity. You say, I have data from mu x1 to xn. I have data from mu, data from nu, and maybe I want to test whether mu is equal to nu. Okay, that's what people do in likelihood-free inference these days. Okay, so they want to know what laws govern the universe. They have a simulator, and they have some observations of the real universe. They have observations of their simulated data, and they want to find the parameters that align them perfectly so that the distributions of the observations and the simulator are the same. And in this is actually just a test for homogeneity, meaning do they have the same distribution? Okay, and here you could just say, well, I have a good idea that this Wasserstein distance between mu n and nu n, which are the empirical distributions associated to the data, should be close to 0 if the data are the same. I mean, of course, I need to understand the fluctuations of this quantity around the Wasserstein distance between mu and nu, but I could use this for testing. I could, of course, once you do testing, you can do estimation, right? So how do you do estimation? You can just say, I'm going to try to find the parametric model that's the closest to my data in this Wasserstein distance, rather than using the KL divergence, which people use in maximum likelihood, or estimated KL divergence that people use in maximum likelihood. And there's another thing that people have been using, which is a bit less obvious, and they've used this and some structure that comes out of Bernoulli's theorem to define some notions of depth and quantiles and ranks, but in multivariate settings. So this is work by Chernozukov et al., and that's still being defined. And here, this is really all that fits on my slide. There's lots of different things you can do. Victor Panaretos here actually has some really nice work in this direction related to functional data analysis. So I'm not going to cover everything. I prefer you ask the expert at this point. Okay, so that's for statistical inference. So let's move on to another application where Wasserstein and optimal transport have been interesting, is geometric data analysis. And really what drives this line of work is the fact that probability distributions are a nice way to capture complex structures. Okay, so if you have an image, turns out you can encode it as a histogram of colors in RGB space, for example. It turns out this captures interesting features of it. Or you can use maybe some lighter data, like the second picture you can see here, and these are basically just a bunch of just a point cloud, and you could actually capture this as just a discrete distribution on those points. Shapes in graphics, it's a very important thing. I mentioned some functional data analysis here. And so when you start doing this, then you have basically a distance between these objects, and there you go, you can unfold your entire machine learning toolbox, because machine learning is a lot about computing distance, right? You can do kernel PCA, and you can do some clustering, and you can do everything that has a distance. You're going to have nearest neighbors. You're going to do information retrieval. You're going to do so many things with this. And this is how a lot of this has been used. Let me just give you one illustration, which I think is actually particularly nice, which is using what's called Wasserstein Berry centers, which is the sum of the minimum square distances to something. All right, so it's basically something that's trying to minimize the energy here. Sum of square distances, sometimes called the Fréchet mean, when you do this over some general metric spaces. So you're just trying to minimize overall distributions, the sum that minimizes the sum of square distances. And this has been used to average complex shapes. Here's an example. This is a weighted average of a donut and a duck and a cow, and you can just interpolate between them. And this is giving you something which is a little more visually compelling, I guess, than if you were to actually average the 3D structure, where however you represent it, let's say a point cloud, that would be pretty awful. Okay, so this is one example. In this case, there's lots of questions associated to this Wasserstein Berry centers. There's questions of computation. There's questions of consistency as n goes to infinity. There's questions of rates of convergence as n goes to infinity. And once you know how to do an average, then you can do a local average, and it's what drives regression, for example. So you could start doing quite a bit of things once you have this notion of average. I like to say that the average is the fundamental unit of statistics, and this is the fundamental of, say, geometric statistics, I guess. A third example, which I think is intellectually quite compelling, and it's the use of optimal transport in sampling. Okay, so sampling is a routine task when you do, say, Bayesian inference. You want to sample from posterior distribution. And for example, one way you would want to do this is if you have oracle access to the grad log of a density. That's typically the case when you don't know the normalizing constant of your density, which is typically the case when you have a complex posterior. You're trying to actually, you can run something which is a discretization of this Langevin diffusion. And you know that this has as an invariant distribution pi. And if you think about the marginal distribution mu t of xt, how it evolves in the space of probability measures, is going to draw a curve which will end somehow at time infinity to pi or 10 to pi. And there's this very interesting work by called JKO by Jordan Kindler and Otto in the late 90s that said, well, in fact, you can view this curve differently. You can think as this curve mu t as following the gradient flow of the KL divergence to pi, but in Wasserstein space. Okay, so when you do a derivative, you have df over dt. And when you do df here, f is the KL, but when you do dt, it's not the usual dt that you see in Euclidean spaces, this Wasserstein dt, something that says that you move infinitesimally in the Wasserstein space. And this gives you a deterministic particle evolution, which will depend on what the current distribution is. It's not completely trivial to implement, but there are some implementation of this deterministic evolution using interacting particle systems, using something called the SVGD, Stein variational gradient descent. And I think this perspective is actually extremely compelling, and it gives you an optimization perspective on sampling, for which you can actually try to use the toolbox of optimization, which is by now extremely well developed, to get maybe rates of convergence, faster algorithms. So we use some mirror descent, and you can try to really bring in the sophisticated optimization algorithms for this. So now I'm going to circle back to couplings. Okay, so we've seen this slide before. Well, not exactly, but when you look at the some optimal transport problem here, the one that's associated to computing the p Wasserstein distance, comes out of it not just the value of your objective, which is your Wasserstein distance, but also the argmin in gamma. Right, there is a coupling that comes out, and we know it's somewhere in the spectrum between the independent coupling and the deterministic coupling. Right, so I want to tell you a little bit what you can do with this coupling. But before that, let's get a sense of what this is actually doing. Okay, so let's go at a very simple example. We're in one dimension, and we have p is equal to 2. All right, so it's just the expected square difference between x and y. They're all in the real line. So I'm trying to minimize this. Okay, everybody agrees this is the objective of 2 Wasserstein distance. Let's expand the square. The marginal of x is given by mu, right? So there's no optimization going on in e mu of x squared, nor there is for e nu of y squared. The only thing you're optimizing is the correlation or covariance between x and y here, just the expectation of the product. So when you do optimal transport really with those two variables, what you're doing is trying to maximize the covariance between x and y. Okay, and that's why it's not so surprising that at the extreme of it, you're going to actually make y be a deterministic function of x. You're trying to really maximally correlate those guys. Okay, so that's what you get when you do this, and you're actually trying to look for very specific functions because you're trying to find functions that maximally correlate. And it turns out that in one dimension, the functions you're going to get are going to be monotone. Okay, so Bernoulli's theorem will tell you that it's the gradient of a convex function, which is monotone in one. Okay, so now we have a sense of what a coupling is trying to achieve. It's trying to somehow, I want you to think about it in simple ways. It's just trying to correlate in an optimal way x and y. We can ask, what do we do about this argument? All right, so let's move on to couplings, and I'm going to show you just a few vignettes of practical work that you can do with this. All right, so the first one is reconstruction of cellular trajectories. Okay, so this is some work coming out of the Broad Institute as part of this Human Cell Atlas. And one of the questions that so Jeff was the leader on this project, and the goal was the goal of cell ontology is to understand how a cell starts from being an egg to a stem cell and then ends up being a sophisticated and specialized cell, such as a skin cell or maybe a neuron. And they're trying to understand, what are the genes involved in this process that goes from root to leaves of this tree. And they're trying to understand what are the environmental factors that come into this complex question that we're trying to understand. But if we can solve that, then maybe we can drive cells to become stem cells or cancerous cells to become healthy cells, etc. So it's important to understand what are the mechanisms to do this. And so basically the way it works is that, you can think, so this is called Waddington OT. So this is where it's coming from. There's this image, this metaphor that Waddington introduced in the 50s. And he said, we can think of cells as being some sort of a marble rolling on this landscape and ending in like, low energy wells in this. And that's how they actually understand this. So we could try to learn the whole landscape. And some people are trying to do this. We're really just trying to understand the blue lines. Like, how do you get from point A to point B? And the way we do this is by understanding, so how do we see a cell? Well, the measures that we do is just by using RNA sequencing. Okay, so you start with a cell, you RNA-seq, so you're going to get a vector in 20,000 dimensions of numbers between 0 and 1. And then we're going to do this along some biological process. So here it's a reprogramming cell, a process. So they start with a bunch of skin cells, and then they just, well, actually it's fibroblasts, and then they just throw some chemicals at it, and they're hoping they're going to turn into stem cells 20 days down the road. And so what they're going to do is at day one, they're going to collect. So they're going to do this to 100,000 of cells. At day one, they're going to harvest 10,000, sequence them. Day two, they're going to harvest 10,000 and sequence them, et cetera. Why do they do this? Because measuring a cell in gene space kills it, right? You take it, you put it in a blender, and then you measure it. But it's not like you could go with your little camera and see how the cell progresses through your 20 days. It's this, extreme version of Heisenberg uncertainty principle. You see the cell, it dies. And so basically here, the problem is that the temporal coupling is destroyed. You don't know, it's not like the green cells are children of blue cells. They're just like the same generations as the children of the blue cells that never got to be born because we actually killed the blue cell. All right, so this is how it goes in terms of probabilistic. So we have basically a bunch of distributions that evolve according to time. And then you can actually observe data, and you're trying to reconstruct the couplings in between. And what we're going to use for this is use this OT coupling based on the principle that nature maybe is not shifting things around like crazy between day one and day two. It's not taking a cell on this part of gene space and throwing it completely on the other side of gene space. And we can do this successfully. So here we're basically doing a bunch of optimal transport between consecutive days. And so this is a 2D representation using UMAP, I guess. So just a two-dimensional representation. And you can see that here we're evolving cells subject to conditioning them to be successfully reprogrammed, which is going to the top left version of this picture, right? iPSC means induced pluripotent stem cells. So this is the successful reprogrammation. So they're starting on day 0 and they're just going all the way there. And we're trying to understand at each step of the way which path and which fork in the road they decided to take, as opposed to going to this neural part or something. So you can see there's a lot of junk there, right? So there are some cells, you want them to become iPSCs, but some become neurons, for example. Okay, so the way we're really doing this, if you think for a second, is we're doing connect the dots. Okay, so if you've taken any regression class, you would probably be in trouble if you started showing this is my estimated regression function. Okay, now I know this is the life of interpolation and deep learning, and people do this all the time. But now you're saying, okay, I want to interpolate between those points. I'm going to just take my little ruler and do straight lines, and that's literally what we're doing, right? We're saying between 2 consecutive days, we're doing optimal transport, and optimal transport is really a straight line in gene space, or in Wasserstein over gene space. And what you might want to do is to get maybe something like a smooth curve, maybe like a interpolating spline. And so you can do this, all right? So let's remind ourselves what a spline is doing. A spline is a curve that minimizes the curvature, okay? So it's minimizing the integrated curvature squared over there. And so if you want to move to Wasserstein space, you have to define a covariant derivative. So it has formally the structure of a Riemannian, formally Riemannian structure. So you could actually write everything. Okay, so we're not going to go into the details of this, but it's a hard problem to solve. Okay, we don't know how to solve this. And what people have done is they've actually done some sort of a relaxation, which is rather than actually solving this problem over the original space, they just relax it over past space. And so what you want is to find a distribution over path such that in average, their curvature is minimized, okay? So here's a bunch of Gaussians. And if you look at what's happening in between each cell, in between each trajectory, it's all a straight line. So in this case, it's basically a distribution over straight lines. So each value for each straight line will be 0 for the curvature. So in expectation, it will be 0. So you've definitely successfully minimized this. But if you think about this in terms of cellular trajectory reconstruction, it's complete nonsense, right? We don't want things to start to go anywhere. So this is an example where we have a sort of satisfactory mathematical solution to this problem, but it does not really solve our trajectory reconstruction problem. So what we did is something very simple. All right, so here's the idea. We said, okay, let's just do something super simple. We're going to do an optimal coupling like we did before. Okay, so you couple from day 1 to day 2, day 2 to day 3, day 3 to day 4, etc. So now think about some rounding of this coupling where each trajectory is mapped to a single, sorry, each cell is mapped to a single cell on day 2 and a single cell on day 3, a single cell on day 4. All right, so that's the trajectory of a cell. So now this is just lining up a bunch of points, and now I'm going to interpolate those points with a spline. Okay, so this ST is basically saying at time t, just output the spline between those points. Okay, so now I have a bunch of splines, one for each of the say starting point, and this is what they look like on this graph. So this is much more satisfactory. In fact, you can prove they don't cross those lines, and so each one is in fact the kind of thing that you would want. So you compute the OT maps, and then you just interpolate between the successive OT maps between optimal transport maps between x1 and t of x1. So what's its target is at day 2, it's targeted as day 3, etc. So now you have these points, you do the spline interpolation. So it sounds like a simple heuristic, certainly deterministic and gives you some nice path. It's very cheap to compute, but it turns out you can prove that this coincides with this Wasserstein splines in dimension 1, or you're minimizing the integral square of the derivative, of the covariant derivative. So it's actually very nice. In higher dimensions, it's more complex, and sometimes it will work, sometimes it will not give you the right thing. And what's nice also is that it's so simple that we can generalize it to higher dimensional splines, like this so-called thin plate splines, where you're trying to find some surface of minimum curvature that actually goes there. So you're trying to minimize the Hessian version of the covariant derivative. And so you can just do it to do some two-dimensional interpolations. Okay, so this was part of I guess an extension of cellular trajectories. We're still in the process of implementing this for real cell data. And I would like, are there any questions about this biological work? So I'm not a biologist. I can try to pretend, but I certainly am not. But I hope everybody understood how we use optimal transport for this. All right, so here's another example. So this is again coming from biology. It's called batch correction. So there's this effect in biology that when you actually take tissue and you do single cell sequencing from the same tissue, same place, everything the same thing. You just take a piece of the muscle and you sequence it, and then you send the same tissue to a lab you do it in the US, and then you send the tissue to a lab in Europe, for example. From exactly the same thing, you actually get this shift of data. And that's just like slightly differing experimental conditions. Maybe the technician is a bit different. Things, there's just this like systematic shift between them. And here we'd like to use optimal transport to remove that shift. The problem is, if I do optimal transport between the blue and the greens, what's going to happen is I'm going to overlap them perfectly. And then I'm going to lose the fact that I had two data sets. I'm going to basically say, well, it's really just one data set and everybody's exactly on top of each other. So I want to have a map that moves from one to the other, like an OT map, but I want it to be somehow regularized. I don't want it to actually map the first distribution to the second distribution. I want it to map the features of the first distribution to the features of the second distribution. So I'm going to forego the fact that it's a valid push forward map, but I still want it to be optimal in some sense. I don't want to put too much effort into distorting one data set to the other. Okay, so we want to be able to do this sort of batch correction that sort of aligns the data set, but keep their own idiosyncrasies. And so what we do here is we privilege something called the low rank coupling. I'm not going to go into details, but it's essentially something that says rather than minimizing over all possible couplings, just take low rank couplings. And we applied this to some single cell data. So the idea is that you have two data sets and you're basically matching one to the other. One data set is labeled, so what kind of cell type it is, and you're trying to predict what it is on the shifted data set. That's really the heart of what domain adaptation is. And in that case, you actually get some very competitive results compared to really tailored tasks for domain adaptation, where we're really just implementing this factored optimal transport. Okay, so really this idea of having two data sets and recombining them into one while maintaining their idiosyncrasies is another task we can accomplish with optimal transport. And finally, I wanted to talk about this project on isotonic regression. And so isotonic regression is a very old statistics topic where you're trying to learn a regression function. And isotonic means it's monotone. All right, so I have this data, I have this data, I have a bunch of points, and I'm trying to learn a monotone increasing function through this. This is the quintessential shape constraint statistics, or I mean, it's part of non-parametric statistics. You're going to get typically non-parametric rates for this, but since you're in one dimension, it's not very expensive. But I want to actually make this problem harder, and I want to make it uncoupled. Okay, so start with the same data points, but rather than seeing the scatter plot, really all I'm recording are the X values and the Y values, and I'm forgetting where they actually came from. Why would you want to do this? Well, think about X being your income and Y being your house price, for example. Okay, I'm trying to predict the house price from income. Very likely it's going to be an increasing transformation. So I could go and ask to every one of you, what is your income? How much did you pay for your house? Or I could go on a census data and collect like 1 million data for income. And I could go on Zillow and collect 1 billion prices for house prices. And the question is, if I can do this, I have so much more data at hand. If I can solve this problem, then maybe I can actually just use much larger data sets that are not collected in controlled environments. There's other reasons why you would want to do this, maybe because of physical constraints or the cost of data collection, obviously privacy, et cetera. And you can think of other examples where you're really trying to integrate two data sets that were never meant to be put together. So here it's important that I know it's an increasing relationship. So the question you should ask is, can I even do this? Okay. So clearly, if I have no noise, then yes, I can do this. All I have to do is sort my X's, sort my Y's, and I know that the original X was associated to the original Y. But the problem is that if it's not, and this is also telling me that they have to be increasing, otherwise there's no way I can recover this. But also if I start putting some noise, then everything is going to be wrong. I'm going to start getting some bias. I'm going to start matching bias. Yeah. Yeah, I could do, you mean in the noiseless case? Yeah, so you could do some optimal matching there as well, and then you're going to end up with the number of sample, which is just the smallest of the two sizes, and that's still going to be valid as an interpolation at least. But you're going to have some points that are not getting any marriage. Okay, so this problem is not, we're not the first one to study it. People have studied it in the 80s. It was called broken sample under linear assumption. I love this quote from this paper that says, like, the dog's walking on its hinder legs. It's not done well, but you're surprised to find it done at all. And it's been studied under very different names, as you can recognize the name on the first line over there. And it's been called permuted data, shuffled label, unlabeled sensing, etc., or learning without correspondence. And it's actually just a cute problem. Like, people are, I think, study this mostly because it's interesting. You can't even do it at all. And so basically, we use again Bernier's theorem, which tells us that the optimal transport map is the gradient of a convex function, which is 1D, meaning an increasing function. So we can actually do this, or monotone function. And what we get is the following. So let's just see the benchmark. If we had the real coupled data, we would converge at rate n to the 1/3. This is classical result from the 80s. And this is the rate that you get. It's in fact optimal. So it's a terrible rate, 1 over log n over log n. If you have noise, you can use OT, and it's telling you, yes, you can do it, but it's going to cost you exponentially more data to actually solve this. But just the fact that you can do it and that OT is a way to do this is actually pretty remarkable, I find. All right, so what are the takeaways? Well, I wanted to say that you can learn OT to couple data. So I think it's a new type of data where you have just a bunch of points on the left and a bunch of points on the right, and you're trying somehow to find a correspondence in different ways from them. And optimal transport is a way to do this. We know that noise can be a nuisance, and it just takes us into some non-parametric rates, even worse. That was actually the rates we saw were non-parametric rates of deconvolution. And the problems can be at very large scale, right? I mean, those single cell data were pretty huge. All right, so I'm actually, how much time do I have? 5? Okay, 10. All right, so let me tell you a little bit about how to learn transport, like what is involved in actually learning those maps. I gave you a bunch of points, I did some matching, but what are the rates? Like, can I hope to do this? Because if you're machine learning, I'm just throwing at it. I'm going to run some experiments, maybe it's going to work well. But as a statistician, I want to make sure that I have the right amount of data to be able to actually get something meaningful. So you can actually think of optimal transport as an energy minimizing thing in the space of curves. They're going to start with a bunch of particles, think of gas particles at time 0, and I'm going to just run them through some, some dynamical system, right? So xt dot is ut of xt, and then what I'm trying to do is to minimize the amount of energy I had to put in that system. So the squared norm, the expected square norm of this ut, I had to put it, so I end up in a particular configuration at time 1. Okay, so I have this thing, they're moving around. I'm trying to find what is the dynamic that's going to minimize the amount of energy I have to transform one configuration to the other. And this should ring a bell, right? We just said nature is probably lazy. Nature is probably trying to solve that problem when it's evolving those cells from day to day. And the answer is the following. It says straight lines, it's called an OT coupling. So he's going to just couple the data according to optimal transport. And then along all these like coupled points is going to just draw a straight line. So all these guys are going to travel in straight lines. Now, nature might be doing this, but also it could be that, there's things that we might not understand in the process as complicated as single cell in gene space. And so rather than having just this deterministic evolution, maybe there is also some noise that we don't understand. So let's just put some Brown in motion on top of this. And things are moving around. And I'm still asking the same questions of minimizing the energy that I have to put in that system to get to the last configuration, while also battling against this this Brown motion that's trying to put me in any direction, right? It's just saying, okay, you want to go there, I'm going to push you there, I'm going to push you there. And so I'm like trying to, it's this control problem where I have this noise that comes into there. So I'm trying to go from here to here, and this is a problem that was actually posed by Schrödinger in the 30s. And there you can actually show that the solution to this problem is in fact some optimal transport with some entropic penalty. So there's this scale divergence there. And if you take, for example, so here, this is this gamma here, which is the intensity that I put on my penalty is basically just driving the size of my Brown motion. Okay, and so the Schrödinger problem tells me that the coupling that emanates, so the optimal transport problem here with this entropic penalty is not telling me anything about the shape of the lines, but what it's telling me is who's going where. Yeah. I cannot change. Yeah, so okay, so this is an optimal control problem. So you should think quadratic programming kind of thing, right? So you know where you're going. So if you're going to plan ahead, you're going to have to predict all of this, right? Remember, this is an expectation, right? But yeah, it's something. I mean, it turns out that the trajectories you're going to be making are actually Brown bridges there. So there's still some randomness in the trajectories, but the coupling itself is going to be that coupling. So the coupling will tell you where I'm trying to go. And with some probability, you're going to go somewhere, basically. But it's not deterministic, right? It's a coupling, right? So each point will go somewhere at random, which is determined by this. But yeah, I mean, if you were that particle playing that game, you would actually react to the noise and say, oh, you pushed me there, I'm going back there. Okay, so now this is the problem I want to solve, okay? I believe there is noise, and I want to actually change my problem. So what I'm going to do is I'm going to do it with data now. So what does data do? It's telling me that I have a bunch of observations, which are basically empirical measures. And when I want to solve this problem, it looks as follows. It's this linear objective, a cost against a matrix which has the right rows and columns. So just doubly stochastic matrices divided by n, essentially, minus this 1/eta entropy term, okay? And then there's an extra constant that's just depending on this product measure. It doesn't really matter. So this is the problem we're solving. It's like an entropically penalized linear program. That's what you need to remember from this. And for this, Couturier proposed this as a solution to just solving the linear program itself. And he used this as a device with a very large value of eta to actually solve this problem quickly and simply. Why? Because if you write the first order optimality conditions for this, you will see that your solution has to have this form. So you take e to the minus eta cost, and then it's just post multiply by a diagonal, pre-multiply by a diagonal. And what it means is that if you can adjust your rows and columns individually so that you actually have the right marginals, you've solved your problem. So there's a natural algorithm that comes from this. It's called Sinkhorn algorithm, which says, well, let's just try to adjust the rows first to match R, and then adjust the columns to match C, and then that's going to screw up my rows. So I'm going to go back to my rows and my columns and my rows and my columns and my rows. And in the end, this will converge. This is what Sinkhorn proved. And in fact, in time, we understood that this was doing something as fancy as alternating breakneck converge projection or block coordinate dual ascent. So it's just a block, you're just basically projecting in the dual to solve the problem. And this was actually improving significantly the speed of implementation of optimal transport, which has really contributed to people using it in practice. In fact, it was so fast that Couturier called it light speed. And with little, I think it was a good name because we had no idea what it meant at the time, but it turns out what it meant was that it was running in near linear time in the input. So we proved that a few years later, showing that you get an epsilon approximation in O of epsilon's cubed iterations. And so basically, since each iteration costs you the size of the cost, so you get O of n squared, then there's some logs that come in there, and then you basically run in something which is the size of the problem. And that allowed us to, have practice and theory actually compare with each other. All right, so the improvement was basically going from quadratic, so from n cubed, so from super linear to linear. But there's also another value of entropic regularization, which is something that Linnaeus has worked on, which tells us that if you actually allow eta to be a constant, not something that goes to infinity, you can actually get something that converges at a parametric rate, which is not something that you get with optimal transport. Optimal transport, you get non-parametric rates. And so the question is, can we take advantage of this, right? Why do we actually insist so much on this optimal transport when we have this minimum energy interpretation that comes from the Schrödinger problem? So I'm going to set this regularization parameters equal to 1 for the true problem and the empirical one. And what we were able to do is to show that, in fact, those guys are very close in some very strong sense. What we showed is that gamma n minus gamma, once suitably renormalized, so it's of order 1 over root n, and in fact, the deviations are sub-Gaussian, just as if you had essentially two averages. Okay, so the couplings, not only the objectives are close, but the couplings are close. And in fact, what you can do is use this to do something which I think is actually very cute. So what does a coupling look like? A coupling looks like a matrix whose entries sum to 1. In fact, each of the rows sum to 1 over n, and each of the columns sum to 1 over n. So what can you do from this? Well, now you have a bunch of observations from xi's and some yi's, and you're going to have a class of candidate transport maps to go from xi to yi. Okay, so let's call it script H. Think of linear maps or smooth maps or deep neural networks or additive maps, whatever you want. And now what you're going to do is you're going to say, okay, my x's were not coupled to my y's, but I have a weighted coupling. So each xi is coupled with each yj with weight wij, which comes from my optimal empirical coupling. And so I'm going to create this empirical loss with like n squared observations, really, n squared pairs. And I'm going to minimize this over my class. Okay, so that's a natural thing to do once you have some weight for each of your couplings. If your coupling was perfect, there would be weight 1 here, or 1 over n, and then this would be xi and the y that was matched to this xi. So that would be perfect. But here we might allow for some weights, and we could say, well, what is the benchmark? Well, it's the one where you're minimizing the same thing, but now it's with respect to the Schrödinger coupling. And when you do this, you can actually show that the solutions of those two problems are 1 over root n close to each other. Okay, so what I'm trying to argue for here is that optimal transport is great, but this is going to kill all your chances of doing high dimensions because it's very non-parametric. But why OT when you can actually use this Schrödinger interpretation, this Schrödinger coupling, which is just another well-identified coupling that has some good motivation in terms of energy minimization, and then use this to actually get parametric rates. And I think this is really, in the first part, we try to motivate this use of entropic regularization as a computational trick to mimic the true OT distance. And in fact, I think its value is more in the statistical regularization. And in particular, we should not let eta go into infinity, but just let eta be this constant value. All right, so I'm wrapping up my talk late, I apologize. So in summary, I wanted to say that OT is appears in many statistical questions like inference estimation, sampling, We mentioned geometric data analysis, single cell data analysis. There's other places that I didn't mention. Causal inference is a big one, fairness, privacy. So you see optimal transport. Some of it is because people want to use optimal transport. Some of it is because it really comes out naturally from these problems. But I think it's really this idea that what makes it really powerful is this ability to couple uncoupled data sets where we didn't really have any tools to do this before. And domain adaptation, I think, is the most direct example of this. And one of the messages that I tried to convey, and I hope it went through, was that we should probably go beyond optimal transport to get some statistical regularization. Here I used entropy, but maybe you can think of something even better than this. And on this note, I will end. Thank you for your attention.
Many thanks, Philips. Would you like to take some questions?
Yes, please. Any question?
Questions in the room?
Yeah,
I'll give you the mic, like this. People get you online as well.
So a question regarding this light speed,
Yeah.
So then you say, now you know because it's n squared. But n squared, in practice seems pessimistic, right? If you have like an Euclidean space,
That's
like
right.
input size would be n.
That's right. And that you can do. So you can also do, so there's actually some follow-up work on this by Jason Altruller, my co-author, and Alessandra Rudy, Francis Bach, John Nalsweed, I think, was involved as well. So my two co-authors. So they, and basically they showed that if you're in low dimension, you can actually run in O of n, but x spin d. So basically you have to choose your rattle, right? So so it's like, I don't know, 2 to the dn or something like this for the rate of convergence. And so in low dimension, yeah, you can use this, and they use something quite different. It's still Sinkhorn based, but really the idea is that so you have this e to the minus eta c matrix that you're trying to scale, and what they do is to find some sort of a low rank representation of this. Because when you're in low dimension, in fact, this matrix has a low rank, and so I think they use Nystrom for this particular case. You don't have to use Nystrom. There's other examples where you can use, if you have, like, for example, if your points are on a grid, you can use Fourier analytic techniques that go really fast. In fact, I claim that this is what makes it go fast, but the fact that you can do this matrix product super fast was really what allowed them to do this fancy pictures with the donut and the cow. And that's because they were able to use Fourier transform. So they were even log there. So that was really fast. And so there's lots of engineering additions that you have to put there to make those things run really fast.
Any other questions, follow-up questions?
Thank you. Thanks, Philippe. I had a question. At some point, you had two plots with a T-SNE plots.
Yeah.
I don't. Maybe you can go back to those if it was a while ago. And then I was wondering, just so you had two data sets and you embed them in 2D for representation.
That's right.
And do you compute this embedding based on the two data sets like joined together, or do you compute them separately and then you overlap them?
You mean this one?
Yeah.
Yeah, so this is actually not from my paper. This is from that paper. And they're not even using OT to actually solve this. They're using something based on CCA that, just like good biology paper is very hard to actually understand from the methods section. So I'm not entirely sure. My guess would be that they're all embedded in the same T-SNE plot.
Okay. So my question was going to be about how we can use the distance in there, but then if this is not based on optimal transport, then it's
oh yeah, okay, so that's also another good point. So in the so this is again so the way we typically do this is that we first do a dimension reduction. So genes live in 20,000 dimensional space typically, and we're not going to run like Euclidean distances between cells in this space are meaningless. And actually, when they were telling me they were using Euclidean distance, I was like, this is insane if it works. But what they do is they first do a PCA. They reduce it to something from, say, 20 to 40. I'm not entirely sure, but that's the order of magnitude. And then on this space, they actually use Euclidean distance. But it's actually also a direction of research that people are looking at, like, what is the right ground metric that you should be using there? I know that I saw a paper recently by Botu that was using even some hyperbolic distances actually to put things apart. So maybe this could be useful for optimal transport. But yeah, the ground metric is an important parameter to tune, and that's something that's definitely swept under the rug. Good point.
Thanks.
I think there have been some questions online. Could you just raise your hands, please, if you have questions online? Like this, you can maybe unmute yourself. There was Yaping Xie and
Hi.
Hi.
Can I ask my question?
Yes,
Yeah,
I can hear
please.
you.
First, thanks for your talk. I just want to know if they have some noises such that the size of the transported data, I mean the second data, is somehow different from the first data. Is it possible to still use OT to find some mapping between these two data sets?
Oh, I see. So yeah, so there are various attempts to do this. I know Lek Heng Lim has one. I think actually McCann himself has worked on this. So indeed, one of the things that's happening when you do optimal transport is that you have to have a ground space with a ground metric, and in particular, everybody lives in the same space, and you need to be able to measure distances between those objects. And so if you have a family of objects that lives in dimension 2 and another family that lives in dimension 4, it's not clear how you would actually compute their distances. So there's several things you can do, and people have tried to address this problem full front, but typically what people do in that case is they use something which is called Gromov-Wasserstein, which is sort of a double relaxation of Gromov-Hausdorff. And the idea is to say, okay, I can think of my point cloud not as like points in this particular position, but just as a metric, as a space that's just the pairwise distances between those guys. And then I'm going to think of my second space as the pairwise distances between those guys over there. So all these things require only a metric on the first space and a metric on the second space. And then I can try to do a matching, which will make those distances as close together as possible in average. And so that's the Gromov-Wasserstein approach. And people have used it in a variety of things, including in single cell and also in graphics, which is one of the spectacular successes of optimal transport. It's non-convex, so now we're no longer in the LP world. Certainly not going to be near linear, but there are some tricks, actually entropically regularized based tricks that actually work pretty well in practice. There's some interesting open questions in terms of why do these things actually in fact work. But Gromov-Wasserstein is, I think, actually one of the most flexible tools arising from optimal transport, because it really does not require to have this ground space that's well done. And if you think about it, it's very close to what Tisney is trying to do in a way. Tisney is trying to locally match distances between points, and this is what or even SNE, not even Tisney, SNE is trying to do that in the first place. And so that's what Gromov-Wasserstein is trying to do. What Gromov-Wasserstein has as a difference is that it's very non-local. So it turns out that when you try to do Gromov-Wasserstein, the large distances are very important to actually do this matching.
Thanks a lot.
Thank you very much. Are there other questions online?
Yeah, so may I ask a question?
Yeah.
Okay, so first, thanks for the great talk. And my question was, so you defined the splines for the in this Wasserstein space. So are these mappings, are they deterministic, like Monge's mapping, or like are they more like stochastic, like Schrödinger's problem? So
yeah, so to be able to define this, we actually define them deterministically. So we actually really need to minimize. Sorry, where were they? Yeah, so we really need to think of having a deterministic transport map here. See, there's like, I wrote compute OT maps between mu I and mu I plus 1. So for example, if I had more points at time I plus 1 than at time I would not be able to compute this map. So this is something that's actually slightly idealized. So we're actually the statement that we make that those correspond to the one-dimensional notions of spline that's in the population case when everybody has a density and those things exist. Now that now that I've given the entire talk, you could actually think of doing a weighted version of splines where, so splines, what's nice is that if I give you the points, there's many ways, you could use de Castaldo's algorithm, or you could use, I mean, it's just a degree 3 polynomial, right? So it's pretty easy to fit. But if you actually go back to the original variational formulations of Euclidean splines, right, the one that's at the top, now what you could do is to actually use those W, I, J, K, L, M, N, etc., put it in this variational formulation and try to minimize over all those, weighted energies among all curves. And this is not something we actually studied, but that's what I would actually try to do if I had to really deal with like couplings that are not actual functions. But yeah, that's a good point. Yapping, good catch.
Thanks. Sorry, just one last further question. So here you study kind of the interpolation of given samples. Do you think there's any way we can do something like extrapolation? Like we're given the data for the first 3 days of the cells, like we can somehow predict what's going to happen in the fourth day. Do you think, is there anything that we can do within this Wasserstein or optimal transport framework?
I mean, I guess, but just like any extrapolation, right, it's going to be subject to all the pitfalls. Like even for vanilla regression, extrapolation is something that's somewhat controversial. I think yes, in a way. So if you go back to this Schrödinger formulation, where you had this drift that you were trying to minimize the energy of, moved along some diffusion. Then from there, if you actually start really going back to the original diffusion model, which I think is what this paper by Hugo Lavenant and Jeff Schibinger that I mentioned at some point, they're really trying to find some diffusion models for which these optimal couplings are actually recovering the right temporal coupling of those guys. Then in the limit, as the step size goes to 0, I think maybe with those, by imposing some additional structure on what your drift would be, you could have a chance of doing there. But this is really not something I've thought about deeply. So yeah, don't quote me on this. I'm not entirely sure. Yeah. For extrapolation, you're going to need some modeling assumptions on what those curves have to be, right? So
right. Thanks a lot. Thanks.
Sure. Would you like to take a last one? It's the last question, maybe in the audience, online, offline.
Oh, you promised an aperitif.
Yes, I did. Doesn't look like so. Then just maybe let's thank Philippe again for his talk. So many thanks. It was a very inspiring talk. Before you all run out and get the apero for those who are offline with us here, just let us remind of the upcoming events. We have Professor Eduardo Charbon speaking next week on photon counting cameras for quantum imaging applications. Same time, 3:15, but different room, INF 328. I hope to see you there. There's also small apero again for those who will come in person. And then on May 2nd, we're looking forward to hear about Josie Yute's work. She recently joined EPFL as a professor. And now please let's meet all outside for the drinks. And thank you to all online for having been with us. Goodbye. Merci beaucoup.